Elisabetta cerca di portarmi queste cose e le leggo in tempo reale, assumendo che
era solo questo quello da rivedere, quando io ho mettuto l'immagine che ha aggiunto un pezzo sulla parte di Berinzi. Poi qui ha aggiunto dei link e abbiamo aggiunto le informazioni quelle della registration fee chiaramente ognuno dei due poi ha dei due comitati ha quell'email che è stata vista, una per l'uno e una per l'altro.
sì, esatto.
Ho corretto le date, 13-17, in quella dell'ICC ho riaggiunto la frase quella che Chiari aveva detto.
Sì.
Quella che, dato che vengono da nazioni diverse,
sì. Sì.
E in copia nascosta elemento di mettere quel giornalista,
sì,
queste anche,
sì,
oltre che chiaramente la Ok, allora la seguisco dalla sua posta.
Sì.
Così rispondono a lei.
Quindi tutte e due.
Sì, cioè sia lei che il segretariato, copia esplicita e copia nascosta chiaramente la mailing list e il giornalista.
Va bene.
Ok.
Buon lavoro.
Grazie. Ora sottolineo la
Stiamo
cosa.
just announcing the next course, not course, the knowledge meeting. And we should hear from the 13th to the 18th of July. In that period, Pescara is particularly active because people can go to the position. And I hope very much that this will represent for the first meeting after this very difficult period, and that people will not feel chosen. And we have been trying to interest very much Marta to collaborate with ICRANet in two different fields. One is the student working on the fast radio burst. She's not, both on the fast radio burst because we are proposing a collaboration. One you is not here. Between when you will assume will come here, and if the worst come to worst, we will have dinner with him tonight. And also, she's visiting. Where are you?
I'm here.
Good. She's visiting from our center in Ferrara. Come here. And we will have dinner with you actually tonight. And then we are collaborating on this idea to possibly look for anything associated with fast radio burst, using both the data of fast and the data of the optical telescope from Sardinia. And we have presented such a collaboration. But it is a pleasure to have her here, because while we are sitting, we have just obtained some new fantastic results. Really fantastic. One of them she shared with examining some of the library data. And there are two aspects. One aspect is that while in Princeton I started the analysis of gravitational waves on binary system. And this result was by far one of the most successful. And it was done in collaboration with Davis, with a group working on in Caltech, Press and Price, myself, and Jamie Tion. I think a little bit of history you were waiting for a constantly feed with some information. And in particular, today we are going back to some of this work. But they are so different in style. Because they have been developing what we call templates. And the developing templates, it has become an industry. It has become an industry. And that is fine. There is nothing against industry. And in particular, there has been one step which has been crucial in this industry, done by the one which I consider my best student for a while, which was because today we are reaching a turning point even in that field. Today, before allow me to say a few words, we are reaching a turning point. Of course, Thibault was the one who invented the one-body solution. The one-body solution, one-body approximation to study gravitational waves in binary system.
I didn't know people was your student.
Eh?
I did not know he was your student. He influenced me a lot, along with you, both of you.
Excuse me. Yes, he was, actually was not my student. He was my postdoc. My student was Nathalie Ruel. And to tell you the story why it's so interesting is because not before yesterday, Nathalie Ruel sent me 5 papers which I gave to Daniele Gregori's print and to read. All of them come from the Thibault work, because Thibault managed to study a particle going around the black hole and emitting gravitational waves.
Yeah.
In the post-Newtonian Now, after Nathalie sent us all these papers, I gave them to read to Gabriele and discovered that they had a fantastic result, which we will write, I hope, if you will be good enough to follow my advice, to write immediately. Now, the key point is that if you have a neutron star around the black hole, let's say neutron star 1.4 solar mass, around the black hole, either around another neutron star that then they merge, or about the black hole already formed and they merge, the formalism gives you the possibility to analyze, then to remove the spectrum. And what happens of the order of, I don't have the count number, but I will ask Daniele to count the number of universities participating. The order of magnitude is around 150 universities. Order of magnitude. Who should scan the paper? 150 each paper. Now, we are examining this because we studied one case directly, not through keyboard, a particle falling in a black hole. We published this document. And we obtained also through Tionno, I hope you write down this, and that is recorded, that way you will not have an effort to build up your team. I hope it is recorded. And we have also the spectrum. The spectrum and the intensity of a particle plunging. And Shurui, we discussed with Shurui. I said, well, the key point is that there Thibault was considered a particle going in a circular orbit. And we are in plunging, yes, I understand, but why we don't compare and contrast the results? Of course, you have more radiation coming out in the circular orbit, but they are the function. One thing, are you listening or not? Then you will repeat, okay?
No, I'm listening.
Okay, I will check. There are two parts, the numerical factor and the functional dependence on the mass of the particle and the mass of the black hole. What we find is that the function is the same. The numerical factor is different. But today we are looking at another result, that the peak of radiation appears to be the same. And it's a function only of the mass of the black hole. This appears to be from today's work. And this is already something interesting. And you take all this work, yes, they agree. There is a numerical factor different, the amplitude, but the functional dependence is the same. What it means? It means that they did the computation correctly. But it does not mean anything about the physical interpretation either of our particle going in regularly or the other particle, even about the real existence. Because the real existence depends on the fact if they have really made an observation, not purport if there is evidence for a physical manifestation of that process. For the moment, we are answering that question. But there is another problem which I am addressing, is the most delicate one, I'm most addressing in the last hours. And I will have an answer, I hope, by next week. Is there any way that you have a physical process which leads, be careful, the physical process, unlike the one that you will mention today, which we understand that physical process, and we see the results. But is there any evidence for a physical process? I hate to give the question until we don't have the answer. But I think we have the answer. Is there any physical process which may lead to a binary neutron star black hole system? This is a very important question. And the secret is in one of shows we are starting. I close to motivate you when you and Troy and Rita, why we care very much about the system of 220101 and the twin of that system, Rita, remind me the number, 240825. Is that correct?
Yeah.
Okay. We are working with Rita this weekend on this source. Is the twin. And we have another system which we discovered long ago with U13 or 427A.
That is a very long time of this.
Eh?
Yeah.
Okay. And I think the secret of these three sources is that they are not corporal supernova, but they are very supernova. And the physics, scusami di essere inconnesso, ma mi fa piacere che...
I'm your guest, so I'm following your times. It's okay.
Good.
Okay.
Please.
Shall
And
I?
then, thanks a lot because she's collaborating with us on this great adventure of fund observation from Sardinia and from
outside the fast together.
and from Fast. But
Yeah, from faster.
can you add something?
Add something. In the end of last year, we did an application, a joint application with the telescope of Sardinia and the faster Chinese, the biggest radio telescope, because these two they cover different frequency. This actually covers a higher frequency than faster. So together we are going to study the process, the faster radio waves. And I don't know the results yet.
I was wondering whether we knew something or
Okay.
should I use the microphone for the people online? Or?
Yes, maybe. System manager usa il microfono, sì?
Uso il microfono? Sì, se no online non vi sento, immagino. Okay, so thank you Remo for inviting me here today. Thank you all for having me. My name is Marta Burgay. I come from the Cagliari Observatory of the National Institute for Astrophysics, and I am a radio astronomer who has worked mostly on the radio pulsar, mid-second pulsar, as basic binaries, but also pulsar surveys, surveys for FRBs, and this kind of thing. So neutron star related things, mostly observational though. And today I'm going to spend the next 45 minutes or so telling you about the story of the last basically 20 years that I spent collecting data and analyzing them with my collaborators on this amazing system, the double neutron star system, that is extremely useful to test general relativity, or in general relativistic gravity. So as you know probably much better than I do, GR has been tested large and wide with different probes, and all different probes are making GR, testing GR, and GR is passing those tests with flying colors, and they test very different places in this gravitational potential and space-time curvature space, and among the highest and most extreme places in this gravity in this graph is tested by pulsars. The more extreme angle is tested by gravitational waves, but the tests that we do with pulsars are much more precise in some ways. Some of them are something like 2 orders of magnitude more precise than with the gravitational waves, and this is because pulsars, this fast rotating, highly magnetized neutron star that shine these beams of radio waves in a lighthouse-like mode, are extremely, or some of them at least, are extremely stable rotators. So we can use them as extremely stable clocks to measure all sorts of physical mechanisms and to probe many different things. And the way, the technique that we have to exploit these amazing clocks is the so-called pulsar timing method that basically allow us to see how these clocks, which are point masses in our universe, fall into the curved spacetime. Either the curved spacetime of, well, spacetime which might have ripples of gravitational waves induced by binary black holes, and that's what we do with our so-called pulsar timing arrays experiments, or how they fall in the curved spacetime of a companion star, for instance, which is what I'm going to talk about today. And the method that we use, this pulsar timing method, is on paper fairly easy. We have a model for our pulsar, including spin parameters, astrometrics, or positional parameters, and if the pulsar is in a binary, also, of course, binary parameters. And from this model, from these parameters, we can predict the time of arrival of any single pulse emitted by this pulsar. And then, of course, we go and observe our pulsar over longer or long time scales with repeated observations, like usually monthly or bi-weekly observations, to measure those times of arrival in the real world. And so we compare the measured and the predicted times of arrival. We create what we call the timing residuals, so the difference between predicted and measured times of arrival. And of course, if the model describes correctly the pulsar, we will have this kind of residuals. This is time modified to and date versus the residuals, so the difference between predicted and measured times of arrival. And if the model is precise, we will have randomly distributed residuals with a small error, a small scatter around the zero. But if one or more of our parameters, of the parameters of our model describing the pulsar, is not correctly taken into account or is not included in the model, we will see different trends in these timing residuals. So basically, well, the easiest one to understand is, of course, if we have like a spin period which is miscalculated, and then we will have an increasing difference between the predicted and the expected time of arrival, and so we will have a linear trend in our timing residual. So we fit for a linear trend, and we recover with very high accuracy our spin period for the pulsar. If we see something like this, so a quadratic term in our timing residuals, this means that we are not taking correctly into account the spin down of our pulsar. a pulsar. It's a neutron star that rotates, it emits energy, and it emits energy at the expenses of its rotational energy. So we do expect it to slow down in time, and this is what we see in this timing residual plot. If we fit out this quadratic term, we can measure with very, very high accuracy the spin down of this pulsar. And of course, if a pulsar is in the binary system, it will move around the center of mass of the binary, and this will induce some delays in the times of arrival. This is, again, it's not MJD anymore, it's orbital phase, and we can see some, of course, residuals if you're not taking correctly into account the orbital motion of the system. If we do take everything correctly into account, we fit forward all of these trends, which, of course, this is the very simplified version of the thing. Usually they are all together, and you would see points all over the place in this kind of graphics, and you will need to take care of one aspect over different time scales, which may be different from the others. But once we do this work correctly, we recover the flat timing residuals, and we will get a final set of parameters, the ephemeris of our pulsars, which will have, depending on how long we observe that pulsar for, some very, very high precision. Let's see, for instance, the P0, the spin period, we know it for this pulsar at the 18th decimal place. So these are also the position of the pulsar. We know it with very, very high accuracy because of the motion of the Earth around the Sun. If the position of the pulsar in our model is wrong, we will correct for the binary motion of the Earth around the Sun in an incorrect way, and we will see some timing residual because of that. So through timing, even if our instrument has a large field of view and no angular resolution, we can reach positional uncertainties which are very, very small. But in some cases, for some binary pulsars, which usually are the fastest spinning pulsar, millisecond pulsars, the timing accuracy, so the accuracy with which we can measure the times of arrival is so high that if we describe the orbit purely with just the Keplerian description, we will not be able to find flat timing residuals. So this means that we need further physics to be plugged in our model, further parameters, and so this means that we can test this well, it's not new anymore, this extra physics with pulsars. For instance, of course, relativistic gravity, and in particular, general relativity. And a framework, a very powerful framework in which we can do this with our times of arrival had been introduced by Thibault and de Boer, that Remo was just mentioning a minute ago, in 1986, and it's the post-Keplerian formalism, which for GR translates in these are the 5 most famous post-Keplerian parameters for GR, the periastrum precession, omega dot, the 2 parameters related to the Shapiro delay, due to the fact that, of course, the signal of the pulsar has to travel an extra bit when it's behind its companion star because of the curvature of the space-time, and this is represented by 2 parameters: the rate of the Shapiro delay, which is proportional to the mass of the second body in the system, and the shape of the Shapiro delay, which is equal basically to the sine of the inclination of the orbit. So the more edge on the system is, the larger this effect will be. The fourth parameters is gamma, related to the gravitational redshift and time dilation. And then, of course, the orbital decay. PB is the binary period, it's the orbital period, and the shrinkage of the orbit due to the loss of gravitational wave is what we are measuring with this parameter. The beauty of this parameter, of this formalism, is that it's basically operationally defined. These are the 5 parameters for GR, but we can fit the Damore and Deruel parameters from our model and then interpret them in the framework of different theories of gravity. So for each theory of gravity, basically, we can write the equations. These are the first approximation, the first order for these 5 post-Keplerian parameters for GR. as a function of the Keplerian parameters of the orbit, which we perfectly measure, as I showed you before, with pulsar timing. So we know the Keplerian parameters with very, very high accuracy, and the only unknowns in these equations are the masses. These are the equations for GR. Any theory of gravity can be written with these dependencies, well, in different forms, but always depending only on masses and on Keplerian parameters, at least at the first order. So the trick here is we pick our theory of gravity, GR in this case, and if we measure any two, of course, parameters, post-Keplerian parameters, we will have solved the system, we will have determined independently the mass of the pulsar and the mass of the companion, capital M being the sum. We plug the masses in the other equations, and if we are able to measure one or more of the other post-Keplerian parameters through our pulsar timing mechanism, fitting out timing residuals, we can have a test of the gravity. So the first two we use to determine the mass within a given framework, and from the third on, we can measure, we can do tests of the given theory. So we can have up to n-2 tests in this case for GR, with n being the number of parameters that we are able to measure through the study of our binary pulsar. This is usually shown in our pulsar papers through a mass-mass diagram, mass of the pulsar on the x-axis, mass of the companion on the y-axis, where we can plot all of the constraint on the masses that we can get from our timing measurements. Well, the first is simply from measuring the Keplerian parameters. This is the mass function, and we can exclude all this gray area of the screen, of the graphic, simply imposing that, of course, the sign of the inclination cannot be greater than 1. And then we can measure our two post-Keplerian parameters and get the mass out within the framework of a given theory of gravity. And if the third and other parameters cross the other lines in the same point, or in the same area rather, because we have, of course, errors in our measurement, we can say that within those errors, the theory is confirmed. And if not, of course, we can discard the theory. So this was done for the first time with this pulsar, this binary pulsar called B1913+16, which was discovered in 1974 by Hals and Taylor. And it was, so pulsars were discovered in 1967, and a Nobel Prize was given to Tony Lewis for the discovery of pulsars. And some 15 years later, the first binary pulsar was discovered. And luckily enough, this first binary pulsar was orbiting around another neutron star. So we now know of something like 300 millisecond pulsar in the binary system, and just 20 of those now, so like 50 years later, are in a double neutron star system. So they were super lucky in that the first binary pulsar was actually a double neutron star. It was a fast spinning millisecond pulsar, 59 milliseconds, orbiting around its neutron star companion in about 8 hours in an eccentric orbit. And after a few years of timing measurements, Hals and Taylor were able to measure 3 post-Keplerian parameters: the periastron advance, the Einstein delay, well, the gamma parameter, and the orbital decay. With the first 2, they measured the masses, and with the third, they could do this test of gravity. Of course, at the time, the first data ended up around here. They had like 5 years of data before they were able to see this effect. This is the motion of the abyssal nodes as the orbit shrinks. And as you can see, this is not a fit to the points. So the points are the observing points, the observing measurements from the pulsar, and the curve is not a fit. The curve is the GR prediction. So they match very, very precisely. And this is measuring the orbital decay. By the way, this kind of measurement was predicted by Kip Thorne already in 1969, so a couple of years after the discovery of the pulsars, and before any binary millisecond pulsar was discovered. So he thought, well, maybe if we do find a pulsar orbiting another body, we can do this kind of test, which is basically the first proof of existence, although indirectly, of gravitational waves. This test verifies GR at the 0.2% level, and for this test, Hulse and Taylor got the second Nobel Prize for pulsars in physics in 1993. And some 10 years later, enters this new amazing system, which I was lucky enough to discover during my PhD thesis. This is not only a relativistic binary pulsar orbiting another neutron star, but this is the only system in which both neutron stars have been seen emitting radio pulses. So we have two clocks in the same system, which is the first reason why this is an even better and even more suitable system than the Hulse and Taylor proposal to do this kind of studies, but also because they orbit each other in only 2.4 hours, so that the orbital speed in this system is very, very high, so the effects of relativistic gravity are enhanced. And another thing that enhances the effects, the measurements, our possibility to measure these parameters is the fact that we are so lucky that we are seeing the system basically completely edge-on. So the inclination of the orbit that we measured through, I will show you now, through the Shapiro delay measurement is 89.35 degrees. I think we have now actually a refined measurement even more precise than this, but always edge-on orbit. And these characteristics make this system very, very apt for doing this kind of tests. So it took something like, I think, 50 years, or 40 years actually, for all 5 post-Keplerian parameters to be measured in the Hulse and Taylor pulsar. There was a publication by Weisberg et al. In 2016 presenting all 5, with some of which with larger errors. And for the double pulsar, after just 1 year of observing it, after the discovery, we already had this mass-mass diagram with all 5 post-Keplerian parameters. There are a couple of things that I want to point out in this graphic. So there are these 2 orangey corners that are cut out of the plot. These are excluded by not only the mass function that we can measure for pulsar A, but we have a second pulsar, so we can detect the orbital motion also of the second object in the system, so we can calculate the mass function also for the other one and exclude also the top left corner in this graphic from only Keplerian measurements. And again, from only Keplerian measurements, we can, for this system and for this system only, also put another constraint, which is this red diagonal line labeled R. This is the mass ratio between the 2 neutron stars in the system, and it's basically given simply by the ratio of the semi-major axis, which we can measure with which are Keplerian parameters. So to first approximation, this R parameter is independent on the theory of gravity that we pick. So any theory of gravity that has to be confirmed through this diagram not only has to have the curves or the pairs of curves, because of course there are error bars here to cross in the same area, but they also have to cross these extra parameters that we can measure only for this system. And as you can see this here, there's no arrow in the, but anyway, the inset here is the blow up, is the zoom of that tiny little square in the middle where all the lines cross, and as you can see there is a little area in which all the curves overlap, and so these already, after just 1 year of observation compared to 40 in the Hulse and Taylor system, allowed us to test the prediction of GR with very, very high accuracy. But the beauty of pulsar timing is that the longer we observe, the most precise our measurement go, and also the smaller our orbit is, the faster the precision in our measurements increase. So if this was the 2004 graphic, look for instance at the two pairs of curves, for the black ones for the orbital shrinkage. And look, this was 2004, this is 2006, they shrunk quite a lot. And this is 2005, and this is 2006. We published, so after only 2 years, this was the situation that we got. This is an even smaller, we don't even see the little square of which this is a zoom here and now because it's so tiny. And we published this result in 2006, in which we had 4 tests of GR, so more than in any other system, because we have this extra mass ratio parameter. And thanks to the measurement, in particular of the Shapiro delay, of the shape of the Shapiro delay, this S parameter, which is the green curve, we were able to verify in just 2 years GR at a level which is like 4 times better than what was done in 40 years with the Hals and Taylor pulsar. Another thing that I wanted to point out is that the curve for S, as you would expect from what I told you before, that the system is seen basically edge-on, traces basically perfectly or almost perfectly the area excluded by the mass function, whose limit was set by the sin I equal to 1, right? So this tells you that indeed the orbit is completely edge-on. But this was after 2 years, but now we have 20 years of data on this double pulsar. We threw at this system all of the instruments that we had, and we timed its ticking clocks, its ticking signal with some of the 6 of the largest radio telescope that could see it. And this is in the southern hemisphere, it's minus 30, the declination. And with this, well, it's not quite 20 years, but 16 years of data were collected in this Kramer et al. 2021 paper that we published in Physical Review at Letters X. It collects something like 1 million times of arrival from our pulsar collected by 6 different telescopes. And thanks to this amazing number of times of arrival and this amazing data set, we were able to reach the highest precision ever in pulsar timing. And so we know all the consequences that this has. And so the first consequence is, of course, that thanks to this very high precision that we could reach with this huge data set, the GR test is now even more precise. This is the current test. This is the graphic that I showed you before for the Hals and Taylor pulsar. Actually, it's a little longer. It's up to 2015. And up to 2015, the test on the radiative prediction for GR had a precision of 0.16%, while with the double pulsar in 16 years, so much less than this, our precision, the test of our precision at that 95% confidence level is like 1 order of magnitude better. And this is not just because the effect is more prominent, but also because we are lucky in yet another way with this double pulsar system. And that is because it's close enough to us, even though not too close, that we can measure its distance through parallactic measurements, both with timing, because we can see barely the curvature of the electromagnetic wave that arrive at our radio telescope. So we have a signature, a 6-month signature in our timing residual that we can pick off and recover the parallax, but also through interferometric radio imaging. So we do know with quite high precision the distance of this pulsar, and we measure a proper motion which is small, and there are 2 effects. I haven't added the equation, sorry, on this slide, but there are 2 effects that interfere with the intrinsic PV dot in the system, with the orbital decay in the system, which are due to the fact that the pulsar moves and it's attracted, it has proper motion, and also lives in the gravitational potential of the galaxy. So there are external effects impacting on this measurement, that we have to take into account. And given its position, we do know, and given the fact that we know the distance to this system, we can correct for these external effects effectively, and luckily also, they go in two different directions. So one is positive and the other is negative, so the external factors that affect our measurement and then we have to take into account are very small in our system, much smaller than our current precision, which is not true for the Hudson-Taylor pulsar. It's much more distant, so we don't know its distance with high enough accuracy to correct for these external factors, and these external factors, even though with high errors, are even larger than with the double pulsar. So this is why we have this kind of amazing precision and also in a small time. And we can improve on this precision thanks to this, while these tests cannot get more precise than this in the Hudson-Taylor pulsar. So this orbital decay means that the orbit of the system is shrinking by an amazing 7 millimeters per day. So it's like sizable, you could see it almost. And this means that this system will merge, the two neutron stars in this system will merge in only 85 million years. This is one of the fastest merging double neutron stars that we know of. And another consequence of the precision that we have reached is that now, for our PB dot measurements to make sense, to match with GR, we start to need to take into account the relativistic mass loss. So I say that at the beginning that the system is losing rotational energy, so it's emitting energy by emitting electromagnetic waves, the radio waves that we do see. And this is E equal MC squared. This is a mass loss. This translates into a mass loss, which is of that size. It looks big, 8.4 million tons per second, but actually, in terms of mass of the pulsar, is only 10 to the minus 21. And yet, we do have to take this into account now, given the precision that we reached in our measurements. And that's, of course, the first time in which we need to do this. Second consequence of our very high precision is that we now need to go beyond the first order in those equations that I mentioned, because the precision is very, very high. And one of the most precisely measured post-Keplerian parameters is omega dot, the advance of periastron, for which which is huge, it's almost 17 degrees per year. The system, since we discovered it, has gone around one full turn, one full 360 degrees, and the precision that we have is on the 1, 2, 3, 4, 5, 6 decimal place, and to that, actually much before that, we need to take into account only the second post-Newtonian order in those equations, because it enters at a level of like 35 sigmas now. The second post-Newtonian order has more or less 10 to the minus 4, so it enters at the fourth decimal place here in this equation here. So we do need to take it into account. And there is another effect that enters at the same level that I will mention towards the end of this talk, so I'll put a little pin on it because I will come back to that, which has consequences on the possibility to measure the moment of inertia of neutron stars, which is quite exciting, I think. So third consequence of our high precision is that we now are also able to measure higher order light propagation effects. So I mentioned already the Shapiro delay, and I mentioned the fact that we see the system basically edge on, which means basically that the radio beam, the lights from pulsar A, the millisecond pulsar, the fast spinning pulsar, it's passing only 10,000 kilometers from the other pulsar when it hits our line of sight at superior conjunction. This means that, of course, as I was mentioned, the Shapiro delay effects are very big. This is the red one is the theoretical curve, and the blue points, for which the error bars are basically too small to be seen, except for the tops there, are the observational points. So the GR prediction and the observation match very, very well. And this is the level at which they matched in the shape and range. So again, two very precise tests of GR, even though not as precise as the one that we can get with the orbital decay measurement. But actually, if you zoom a little more into the center of this graphic and you subtract the theoretical curve, you actually see that there are some little residuals. So this means that before superior conjunction, the pulses are arriving a little later than what we expect, and after superior conjunction, they are arriving a little early. And this, we can explain this with these higher order light propagation effects, one of which is retardation. So of course, the speed of light is not instantaneous. It takes time for the light to travel from pulsar A to pulsar B, which is rotating in this direction there. So of course, when the light from pulsar A arrives at pulsar B, it's a light that has been fired when pulsar A was not at superior conjunction, but a little earlier, and the same when it goes after. So this is one of the two effects that are contributing to this, but there is a second effect contributing in the same direction and in more or less the same quantity. Oh, this is the net effect. So our curve, the curve that you would expect with just normal superior delay, is the blue one, but taking into account the retardation, you would expect it to shift a little bit. And with previous pulsars, we could not see this because our error bars were too large. But in this system, you do see it with 16 years of data, but you do see it. And the second effect is a deflection effect. So again, here we have the pulsar spinning in this direction, orbiting in this direction around pulsar B, and the B pulsar bends the light as fired from pulsar A as it rotates. And from the fact that we see that the pulses are arriving a little later before superior conjunction and a little earlier after, we can actually confirm that pulsar A is rotating in a prograde way. Otherwise, we would have the opposite effect, and then these two, retardation and deflection, would basically cancel each other out. So through this observation, through this tiny little discrepancy with the only the normal Shapiro delay, we would not see these extra effects. Fourth and last for this slide is the fact that we are now also able to measure not only the 5 famous post-Keplerian parameters, but an extra one, even though with not high accuracy. This graphic here is exaggerated, of course, and it shows that in relativistic gravity, you expect for that an elliptical orbit does not have a perfectly elliptical shape, but it's slightly deformed into a sort of egg-shaped. And this is something that we barely see in our data, but if we did not take into account this deformation of the orbit, the gamma parameter with covariance, with this delta theta parameter, will not match GR anymore. They covariate with each other, so we do have to take into account these in our measurement. The test is like a 1.5 sigma level, so it's not constrained almost at all, but we do have to take it into account. So, okay, if we put all of these measurements together, we can draw our new magnificent mass diagram in which all the curves, except this blue one, well, I don't know if you see it, blue. It was blue, which I will come back to in a minute. All of them seem to be just lines in this graphic, but if you do zoom into the center, you see that they are, again, areas with their little tiny errors. So now we have 7 post-Keplerian parameters measured, including that blue thingy that I'm going to talk about in a minute, plus the mass ratio. We need, as I was just mentioning, we are able to measure next to leading order effects in signal propagation. We have the most precise strong field test in GR, thanks to this pulsar, 99.99 0.87 precision, and so precise that we need to take the mass loss into account, the relativistic mass loss into account, and that was the little pin that I put in the previous slide and that I'm coming back to. We also are able to start to probe the moment of inertia of the equation of, and in turn to put some constraint on the equation of state of new star. Why is that? Well, because at the same level as the second post-Newtonian order enters also another contribution to the omega dot, to the Pescara advance, which was already presented and by, we don't see it, but Moore and Schaefer in 1980, I think. Yeah, it's kind of blurred, sorry about that. And also in this case, as for the second post-Newtonian order, this enters at the 10 to the minus 4 degrees per year level, and it is proportional to the moment of inertia of pulsar A. It has some dependency also on the geometry of the system, but we do have a good handle on those. And so with the measurement with the precision that we now have on omega dots, we can start to put constraints on the moment of inertia. If we zoom into here, what you see is that if we were not taking into account this omega LT, the lens steering part, we would have this line here, which is not what we're measuring, and this is what we are measuring now. This area, this grayish area here, is what we get if we move the moment of inertia for radii from like 15 kilometers down to, basically nothing, or some physical limit for which the speed of sound in the matter would be larger than the speed of light. So, given the error bars on the other systems, on the other measurements, especially the shape of the Shapiro delay and the orbital decay PV dot, we cannot constrain much yet about this. We don't know exactly where this is because of the crossing point of those, but if we are going to shrink those error bars in the next years, we will be able to pinpoint better and better the moment of inertia. So far, we can just put an upper limit, quite large upper limit, which is this red line here. This is moment of inertia, and this is the distribution. These are measurements of the moment of inertia by the nicer satellite, measurement of the pulsations of millisecond pulsars in X-rays, and these I think are from gravitational waves, so of course we are still far from that, but our measurements are going to improve fast in time, and so we will have a proper measurement and a proper moment of inertia, and so a radius and some information on the equations of state of neutron star thanks to this high precision and timing that we have for this pulsar. So the last thing that I want to discuss is this vertical bluish line, which has a symbol which is omega spin B, and it's related, as the name might suggest, to relativistic spin precession. So for pulsars, this was an effect that was predicted in 1974 by Moore and Rem here, immediately after the discovery of the Hall-Taylor pulsar. I think the paper came out even before the discovery paper was out, and this effect is such that, so the yellow arrow, I don't know the colors, everything seems yellow, but the yellow arrow is the spin axis, and it's precessing around the total angular momentum axis, the green one, and of course also the magnetic axis with the radio beam of the pulsar is also precessing in time, so it's changing the geometry, the line of sight from us to the pulsar, to the beam of the pulsar is changing in time. So what was predicted was that, of course, because of this system, we could see different, our line of sight would cross different parts of the radio beam as time went on. And so, for instance, initially we could see a large pulse, radio pulse, because our line of sight would cross like the higher latitudes in the beam, and then as the beam processed away from the line of sight, we would see smaller and smaller pulse profiles, and the pulsar could even disappear at some point. And this is what we actually saw in the slowly rotating pulsar of the double pulsar, pulsar B. All the tests that I showed you up to now depend on the other pulsar, on the fast rotating millisecond pulsar that we call pulsar A. This is instead the slow rotating pulsar, pulsar B. These are pulse profiles from, I think, 2003 down to 2008. And you see the profile is changing. It was single peaked, and then it became double peaked and fainter and fainter and fainter until in 2008, mid-2008, the beam went basically because of this geodetic precession outside of our line of sight, and we lost it. So the GR prediction for the period of this precession is about 75 years, I think, but of course it depends on the shape of the beam of the pulsar, the precise time when it comes back. But even though we don't see it anymore, we can see the effects of pulsar B on the other pulsar, on the one that we have been studying for these past 20 years. And this is, again, because the system is seen edge-on. So what we have is that the radio beam of the pulsar that we have been studying, the fastest spinning A pulsar, when the pulsar goes behind the companion star, passes through the pulsar B large magnetosphere. And so what we see is a 30-second eclipse. So you see here, this is basically the light curve of the pulsed emission, the intensity of the pulsed emission. As the pulsar approaches superior conjunction, you see it's high and then it gets down, gets to zero and climbs back up. But when it goes to zero, when its eclipse is not uniform, the signal is not always absorbed, it has windows in which we do see it, and those windows have either half the spin period of the pulsar in front of it, or the spin period of the pulsar in front of it. So this pattern here was used, the pattern of the intensity of the emission of pulsar A when it passed through the magnetosphere of pulsar B was used to find a geometrical model for pulsar B by René Breton and collaborators. And you can see here, so let me pause this a sec. Oh, sorry, I didn't mean to do this. So what you see here, so the big donut is the magnetosphere of pulsar B. The black dot is the millisecond pulsar going beyond it, and this is the light curve. So you see, you don't see the pulsar, you see it, you don't see it, you see it, you don't see it, you see it. So it peaks out twice every rotation because of the shape of this donut, and then at some point it's hidden for a full rotation, but every now and then it peaks out, and then it's hidden for a little while completely, and then it comes back out on the other side. And by fitting a geometrical model for this donut, of course, the shape of this light curve depends on how it is inclined, how inclined is the rotational axis with respect to the magnetic axis, especially the rotational axis with respect to the line of sight. And so by fitting this, Breton et al. Were able to figure out the correct geometry for pulsar B, but the geometry, because of geodetic precession, of relativistic spin precession, is changing with time. So Breton et al. Had 4 years of data, and they could fit the geodetic precession into the changing light curves. You see there, this is 2004, 2005, you see it's changing the shape of the light curve at the bottom is slightly changing with, and it's becoming more symmetrical in a way. And then they could also predict how it would change in the following years. And as you can see, through this fit, they could not only fit the geometry at a given time, but they could fit the change in geometry, and so have a prediction for the relativistic spin precession. Their measurement was not terribly precise. It was a 13%, I think, measurement, which is this large band. Since then, we have, of course, observed many more eclipses, and we also use new telescopes, such as the Meerkat radio telescope in South Africa. This is again the same light that we see here, but it's like pulse phase versus orbital phases. It's vertical, so pulsar A, you do see it, don't see it, see, don't see it, see, don't see it, see, don't see it, see, don't see it, and it has two pulses just because we are seeing both radio beams for pulsar A as it rotates, because it's an orthogonal rotator on top of everything, so it doesn't. So we are even lucky with pulsar A because it's an orthogonal rotator, so we do not have relativistic spin precession effect on the millisecond pulsar, which would complicate the timing precision of our measurements. So no geodetic precession for pulsar A, but yes, definitely geodetic precession for pulsar B, and thanks to this new observation, we have been able to shrink the error bars by a factor of 2. So now the measurement, which is not a precise measurement because we are not using timing, but this fit on the eclipses, now the error is about, it is a 6% test. And it's amazing because we can do it without even seeing the pulsar itself. We do see its effects. So while we wait for pulsar B to come back, and we have prediction that says that it should come back in 2034, but I mean, it really very much depends on the shape of the beam, which is distorted by the wind of pulsar A and by several things, so it's very uncertain. We are keeping on observing the system with all telescopes that were included in the 2021 observation in the paper, but also with this new Meerkat radio telescope, which is one of the best radio telescopes we have now, together with FAST. I think this is the best for the southern hemisphere, FAST is the best for the northern hemisphere, providing the best precision ever. And we have a former student that has worked on the first 3 years of Meerkat data on the double pulsar, and just 3 years of Meerkat data she was able to measure the second order light propagation effects better than with the 16 years data set. So the scope for improvement thanks to this telescope is amazing, and even more so it will be when we will have the full SKA observatory, which will comprise the Meerkat telescope in South Africa. Meerkat has 64 dishes, SKAO mid, so-called SKAO mid, will have 197 dishes, and there is going to be also another radio telescope, which is again part of SKAO in Australia, operating at much lower frequencies, hundreds of megahertz, well, up to 150 megahertz, which is going to be composed by a huge number, 130,000 dipolar antennas. So the future is very bright and very open, and we will be able to hopefully finally break GR and find that it doesn't work at some level, and new physics is going to be needed. So I'm going to stop here for now, and I thank you for your attention, and I'm going to take questions if you have any.
Inspired by gravity copy, because gravity copy was done to do that precisely
in the solar system, yeah.
Around
Yes.
Earth.
Yes.
And we proposed, but maybe if this phase, we can always go to the sky and see the effect in the library. And this was the paper which we did right away, and we asked the Schnerowitz to publish. Because Schnerowitz was member of the French Academy, and because we published immediately.
Oh yeah, I saw that the title was in French, so the whole paper was in French.
By the French Academy of Science. And this was, but I would like to ask you some other question.
yeah, bear in mind that the theoretical heavy lifting of things is done not by me, but by Michael, and I'm the observational person of the team. But yeah, go right ahead.
But still, when the tail of pulsar appear, we, together with Kramer, I think we predicted that this year it should disappear.
Yeah.
What happens?
So it hasn't disappeared yet. I think the model was correct, but probably the shape of the beam, the actual shape of the beam is probably a little more elongated than what you and Michael put in the prediction. So it's gonna disappear at some point. The shape of the pulse is actually following the track that was in that simulation. But I think I have actually. Let me see if I do have a little. No, I haven't added it, sorry. I had a little simulation showing how the proposed beam should have changed, and it is following that sort of path, but probably it's longer, the beam is longer, so it's going to take a little more for it to disappear.
But we will succeed in this year or not?
Probably not this year, because it's not shrinking as fast as was predicted. So more or less, yes, but probably the beam is longer, and we don't know how long it is. It's not symmetrical, it's not spherical and symmetrical. It's probably elongated, but yeah, soon anyway, in a few years, I guess, we could see it disappear.
I was hoping this year.
Yeah, it would be cool.
The other point that you have made, which you are really seeing the precession in this binary, because one system is gone, and it will reappear again in how many years?
So the full period is 75 years, but of course, I mean, the beam has a size, and we might be seeing both beams of the pulsar. So the latest prediction that was done based on Meerkat data says 1934 as the earliest. Then there are, depending on how the beam is shaped, because we think it's like horseshoe shaped, it's weird. It might even be 2040 or 2050. We are monitoring it. I mean, for what we know, it could enter earlier if it's very distorted and very asymmetrical. But yeah, the latest prediction is 2034.
I think this is a major contribution, which was, I hope everybody is following, especially for the people who are not been participating. But this work of Stanford with gravity copy was very inspiring. And from this sort of collaboration, we can learn more, learn very much. And we are today doing, even in this house, something of the same magnitude. Let's see if there are questions.
I have a question. Yep. So for such very precision test of detecting arrival times, have you ever considered the light traveling speed is not c, but it's group velocity, because the light travel in the mediums, not really vacuum. Mm-hmm. Like what you mentioned, instead of medium effect, because the effect certainly small. Because if this is in mediums, we have a group velocity c, group velocity smaller c, and due to this effective epsilon mu, so on and so forth, and certainly due to this proton interacting with the receiving proton, with the neutrino, with whatever, okay, and this will have a really physical velocity, group velocity, definitely not c.
Yes.
Certainly small, effect small, however distance very large. Mm-hmm. So then I don't know how this is taken into account, because if you test GR, increasing risk. It's a dose neutrality and you expanding by certain order. Okay, then you say you are testing GR in which 99%.
Yeah.
I don't know how to evaluate quantitatively. But now, if I put
It's
this
just the error
question,
bar.
okay, now put these questions. The arrival time, depending on velocity of travel, which is not C, if you consider it's not very, but the majors.
Yeah, I think what counts is not the space between us and the pulsar, but what we can measure is what happens between the two pulsars. So the distance that we can test is small, and yeah, I guess I don't know on that distance what precision we would need, but I'm thinking, where is it? Yeah, this kind of effect here that we saw here. So I guess if C was different, we would be able maybe to see a different effect in this. Let me put the next. Oops, no, not this one. Sorry, the previous one. There. Just a second. Apologies. I wanted to. Okay, here. So I don't know. I'm guessing the effect is much smaller than what we see here. But if the speed of light was different than C, this displacement would be ever so slightly different. So, and well, we now have error bars here. So I don't know how much smaller these would need to be able to test this effect. But of course, I mean, it's in there, but it's probably much too smaller for now to be able to see. I mean, this, because yeah, I mean, we cannot say anything about the travel time from us to the pulsar. What we can see is a difference in travel time from one pulse to the next, and this is affected on the scale of the system, not of the distance between us and the pulsar.
I have a question.
Yeah.
I just wondering the type force, the type information, and it should be enter the 2 or 2.5 force per Newton meter. So have you constrained this?
Not yet. Yeah, I don't know. I mean, for neutron stars, it's tiny effect. Yeah, I think I think for neutron stars is small, and so 2.5. We do have some. So we are starting now to be able to need to add a higher order in omega dot that I was mentioning, in the shape of the Shapiro delay, and in PB dot, but this is, I think, still at the 1.5, if I'm not mistaken. I should ask Michael Kramer, he's the one who knows best. But I think, I mean, eventually with the SKA, we might be able to get to that level. But yeah, not so far, we don't need to take that into account yet.
Certainly, we enter the 2.5. And another question is, what you expected?
I did not follow what you were asking. Can you repeat?
The
Tidal deformation.
Since it's binary.
Yes.
This should enter the 2.5% correction. Another question is, what you expected when this gravitational wave should detect directly by the future gravitational wave detector?
Okay. I don't remember. I mean, it should be detectable by LISA, so the space interferometer. Not maybe those two pulsars are still too far apart. Yeah, I don't remember the numbers exactly of the size of the orbit that LISA can test. I'm sorry, I don't remember. But yeah, it's in the realm, I think, of LISA. Yes, not for the ground-based, it would take like 85 million years. I mean, we will be able to detect them just when they are very close.
So it's possible.
But yes, with LISA, maybe some tighter system than this one, maybe not this one, but we do have a couple of even closer by double neutron star system discovered more recently, which might be detectable.
What is the strength of the magnetic field?
So for the millisecond pulsar is 10 to the 8, more or less. I don't remember the exact numbers, but of the order of 10 to the 8, and the other one should be of the order of 10 to the 12. Even though for the other one, I mean, we were able to make this model of the magnetosphere, which seems to be actually also dipolar, which is good to know. I mean, it works. A dipole works, but it's a truncate dipole because the wind of pulsar A, which is very close to the big magnetosphere of pulsar B, is probably deforming pulsar B's magnetosphere and distorting it. And so by the size of the eclipse, which is just 30 seconds, we can say that the magnetosphere which is participating in the eclipses is about like 1/3 of the light cylinder. So probably it should be much bigger, but it's distorted by A and it's shrinked. And so probably that has some effect also on the spin down of pulsar B, from which we estimate the magnetic field. But yeah, I mean, the order of magnitude is what you would expect for a recycled millisecond pulsar in the case of pulsar A, and a younger pulsar, which is what we would expect for pulsar B from the evolutionary point of view.
And the magnetic field in the case of
it's around, I think, 10 to the 9. Oh yeah, probably also for the double pulsar is a little larger than 10 to the 8. More or less they are in the same area of the PP dot diagram in the magnetic field wise. It's around, yeah, something 10 to the 9, I believe, I think. Yeah, this is a number that I don't have from the top of my head because it's something that doesn't enter the timing precision, so I don't recall it. Yeah.
So how many of those double pulsars do you have?
So double pulsars with both neutron stars seen as pulsars, just the one. And actually not even this one because it has precessed outside of the time side. Double neutron stars with a pulsar and a neutron star that is not seen in the radio waves. We have, I think, 20 plus a couple of maybes, because I mean we have measurements of the companion mass through pulsar timing. It's in some cases it's around 1.5 solar masses. It's not precise enough to distinguish whether it is a neutron star or, say, a CO white dwarf, so a heavy white dwarf. But yeah, on the order of 20 systems.
And for those 20, do you see, I mean, you have them at a significant variation in the redshift, so maybe one can test
no, because you don't have to see that. So redshift, the gravitational redshift, you mean? Yeah. No, we don't see that effect in these. We do measure for 5 or 6 of them the gamma parameter, the gravitational redshift parameter, which is kind of linked to that. But it's both gravitational length, gravitational effect, and time dilation, and gravitational redshift together. So I don't know whether it could be used for that. Yeah, think about it. Yeah, a few systems anyway. But yeah, we don't know. I mean, the problem with pulsars, well, one of the problems with pulsars is that we don't know the distance. We know, roughly speaking, from the dispersion measure of the radio signal, which is affected by the interstellar medium. So we know how much of the interstellar medium has been crossed by our radio waves, and if we have a model of the interstellar medium, we can guesstimate the distance, but it's a parameter that, except for the double pulsars and a few others, for which we have parallaxes, it's not known.
Well, congratulations on that discovery. And also to meet you, so.
I was so very lucky to find this thing in my PhD. Yeah.
What is the period again for all three of them?
So the spin period, you mean?
Yes.
So the spin period for the pulsar A, the fast pulsar in the double pulsar, is 23 milliseconds. And for pulsar B is 2.7 seconds. And the Halsen-Taylor is 59 milliseconds. So Halsen-Taylor and the pulsar A are recycled pulsars. And pulsar B is the second-born neutron star in the system. So it hasn't accreted any mass.
So, any X-ray observational data for this process?
So yeah, I remember back in 2004, we did do some X-ray observation. We did see it with Chandra, I think. I don't remember anything about them though. I don't know. We did see them, not pulsations, I think, just like the dot. Yeah, I don't remember whether, I don't think we saw pulsations.
This is the most accurate case.
So, I mean, we have better constraints from X-ray observations. For instance, there are these observations of the NICER satellite in which they observe X-ray millisecond pulsars, and they have a modeling of the shape of the X-ray beam, of the X-ray pulsations, that takes into the puts, that uses all the GR formalism, and from that they can measure radii with higher accuracy than that.
And even for the single pulsar.
For single, yes, this is for isolated pulsars. Yeah, the X-ray ones are for isolated pulsars, and yeah, I guess for binaries is the only one that we have.
For X-ray ones, how many can they measure this?
So I think they've done it for at least 2 systems, maybe 3 now, I don't remember exactly. I saw a recent paper, but I think it was a better measurement of the same pulsars that they had already, so I think 2 at least. And they are working on more, but it's a complicated business. Yeah.
So, any ideas? Are there any ideas on how the initial conditions of the system like initial, whether such a binary will have initially evolved as excuse me.
We cannot hear you.
Oh,
yeah.
okay. Yeah. Yeah. So yeah, they have an accent. So my question was, are there any ideas on potential initial conditions for a system, binary system like that? Whether it could have evolved maybe both of them as baby stars, like stars before,
Yes.
and a regular, or whether
Yes.
idea from
So the general idea, I'm sorry that I don't have, I had a little animation. Well, the general idea is that this kind of system comes from binary system with 2 massive stars, because of course you have to produce 2 neutron stars in the end. Yeah.
massive stars.
Yes, 2 massive stars originally. One would evolve faster and go supernova, and of course the system needs to remain bound. Then the second would start evolving, transfer mass through either wind or some short Roche-Lobe mass transfer, and that mass transfer would transfer also angular momentum onto the first-born neutron star, and which is the reason why the first-born neutron star is spinning faster. It's 23 milliseconds because it has been spun up by accretion in an X-ray stage of the system. And after it was spun up, and probably also its magnetic field was buried by accretion of mass, the second star in the system would also evolve into a supernova and give birth of the second neutron star. From the velocity that we currently see and from the fact that the first pulsar is an aligned rotator, there have been a few studies that they concluded that probably the second supernova is the so-called electron capture supernova, which gives rise to a lower velocity kick after the explosion, which is why the system has remained bound. So the general idea is this. I don't know if there are more precise simulations that can tell you the initial masses or the initial orbital periods, because many things can happen. I mean, we have to have two supernovas with big kicks to which the system has to survive. So.
I have a couple of questions. Since you mentioned, by the way, this pulse shape, what about you're looking at gyre effects on the time of arrival of the pulse, but what about the pulse shape? Any gyre effects which...
So, yes, we try to look into that. Well, the first would be checking for, also for the other pulsar, for pulse shape changes due to spin precession, relativistic spin precession, which we don't see in pulsar A, because it is an almost aligned rotator. We estimated that the misalignment between the spin and angular momentum axis is about like 3 degrees, so it's very small. You wouldn't expect to see much in 20 years at least, well, ever. And the other thing that we've been trying to look for is latitudinal latitudinal effect in the light bending. So we were looking, there is a paper by Huan Chen Hu et al. In which he was looking at profile changes around superior conjunction to see whether we could see a different crossing of the beam because of latitudinal deflection. But we don't see it yet. I mean, our data are not precise enough in that respect. So maybe with the SKA radio telescope, which will have instantaneous sensitivity even much higher, the profile will be even better, and so we might see something. Because I mean, we do see the longitudinal effect, so we might see also the latitudinal one. But yeah, not yet.
But then you also said this very special system. One is aligned rotator, another is orthogonal rotator, means that the magnetic poles are on the equator of the system.
Yes, yes, exactly.
How this is expected to be formed?
Yeah, well, actually, I don't know. No, I mean, I think someone has looked into it, and there are papers on that. And yeah, one of the ingredients is the fact that the second supernova is probably being one with a low kick. So this kind of, I don't know exactly what these electron capture supernova are, but I mean, they entail a smaller kick. So the first born pulsar, which had probably been aligned also thanks to the mass transfer from the other star, has remained aligned even after the second supernova because it had a small kick. That's more or less what I understood of it, but yeah, I guess we're lucky because yeah, orthogonal and edge on, wow. So I don't know, either we're lucky or there is an explanation that we haven't thought about why this kind of system would be easier to detect or something maybe.
Okay, I think a proposal idea that hold in my mind, but I don't have an answer yet. Is when I'm working on the artificial intelligence, I always worry about the creativity of the machine. Because creativity for human, I think somehow is from the nature, from the uncertainty, from the random fluctuation. But for machine, we use definite number 1 + 1 is 2. Yeah. And even we generate a random number that is from a formula, not from nature. So there's a way you can have a random number generator from the nature. And for computation, for this machine learning, you need a very fast generator. The computer computes faster. And it should be very precise but uncertain. But in my opinion, this timing, this pulsar is the best source of random number generator. I don't know if anyone is working on this or to make a website providing an API for all the people using this random number generator.
That would be cool. No, I have never heard any suggestion like that in this before. So it could be interesting. Yeah, why not?
There is some hidden statistical correlation. You
Between-
will fail.
Oh, yeah.
Because random by definition. So be careful with that.
But then that would be interesting because we might find out some statistical correlation in pulsars that do not talk to each other. That would be super interesting. Like supernova only produce pulsars that rotate at a certain amount, a certain rate.
Maybe like from signal, you have the uncertainty of the signal. But I feel maybe most of the uncertainty of the signal is from the instruments, not from the visual or from
Oh yeah, probably. Yes.
From the instruments, then you have something, you can make this causality with the range of your neural network and the instrument, like with a short distance. But what we want to have is to disconnect the causality. So to have something far away, signal far away,
Yeah.
and continuous, precise.
It's interesting.
Maybe think about it.
One of the reasons I convinced you to come was that you are looking definitely to millisecond pulsars. But they are old. They are old. They are at the last part of the technical revolution. Instead, what we are interested in this house is to a different millisecond pulsar. A millisecond pulsar which happens 1.42 seconds after a supernova. And this object could have a magnetic field much bigger to 10 to the 18 gauss.
Then it will not survive as a millisecond pulsar for long because it would slow down very fast.
Yes, but this is the thing we are studying. Even in that short time, which would be up to it could survive for a while. But still it would be very interesting to understand that physics. And this is the topic we are really working with some team, with you and with Sure. Very exciting.
Yes. Yeah, what are also the observational prospects? Because, I mean, we haven't seen any why don't we see, for instance, a pulsar in 1987A, supernova 1987A? Because I wonder if it's just because it's embedded in so much gas that it's absorbed, so we need to change observing frequency. I mean, it's a challenge observationally, maybe also.
We don't want to explain everything.
But I'm an observation, I want to see them.
to see if we have any observational evidence for this sort of object, which will be manifestation of a fundamental idea which was proposed by Fermi in China. Then is a guarantee that that topic is of interest. Next time that come, I hope to consult on the progress of ICRANet, if you will be selected as Italian representative in ICRANet scientific committee, we will keep also discussing this topic. But somewhere...
You're not revealing too much so that I accept.
Excuse me?
You're not revealing too much so that I need to accept in order to know more. No, I'm kidding.
No, but this is something to tell you that we are currently today.
It's very interesting, very intriguing.
Okay, just to advance. Well, thank the speaker very much. I think somewhere on the line, the work done by Gravity Copy should be recognized as stimulating in this field. Okay, thank you so much, and we will keep discussing.
Sorry. We remember replication rate data out of more than 100 events. Only two, the spin axis not aligned. Only one in after the spin, some very large angle, but mostly spin aligned and not parallel, not very close to. So your double pulsar, the origin, I wonder how we form it. Oh, yeah. Formation, evolution process of these spin axes. And level is if we have X-ray precise observational data that can be used as laboratory QED test bed by measuring X-ray radiation rotation when the X-ray from beyond one of the pulsar pass through strong field of the other pulsar and spin rotate, X-ray spin rotate. The rotation angle proportional to inversely proportional to wavelengths. So when you have X-ray, precise X-ray observational data, then they can be used to test strong field field in theory. I thought for that happen because that can be a good test bed. Yeah, I know. So when we have X-ray data,
X-ray pulsar is another type of pulsar.
There are few pulsars that are both X-rays and radio.
Yeah.
Usually the pulsars are
Actually,
but we do have some.
not a whole X-ray. The neutron star beam through some probing X-ray, X-ray observed by some satellite. The detector then just measure the spin rotation of X-ray passing through and within 12
I
hours.
think I need you to discuss, and I need something urgent.
I think I need to do some bureaucracy.
Yes.
But
Oh,
yeah.
And you can use
coordinating committee comes to just the board or send me message that it will not join, so it will not come and attend. So contact point. Yeah. He's interested to work on this first observation. Yeah. Would you replacing?
We were trying to send the organization was sent to all the committee.
Oh, really?
Yeah, but let's check. I think it's possible to adjust.
Yes.
Just because
Yes, they are usually pulses from radio pulsars are even 30% polarized. So this is also the change in the polarization angle across the radio beam can be sometimes huge. millisecond passer data ones, it's stranger, but for the slow ones, you usually see S-shaped change in the polarization angle, which traces the magnetic field lines. You can from that do some. So we do have data on this. Yes. Great. Because actually I'm working on also new physics, axioms. All right. Yes. And actually axioms can affect the propagation of light. They can affect the polarization of the light. Okay. Yeah. And actually I'm trying to use the polarization data of fast radio waves to put constraint on the transfer space of axion. Okay. I wonder, does it make any difference the fact that, I mean, fast radio waves are extragalactic, so you have a larger space to cross, while pulsars are just galactic? Does it makes it less useful, or does it matter? I know nothing about that. Actually, axioms, their strength depends on, it is local. I think near the source, the field of axioms are not as strong than here on the Earth, where we observe the observation time. And actually the phase shift of the polarization angle depends on the difference between the strength of the axioms in the source and on the observation on the Earth. There's a difference between these two. So we need to choose an environment in which a strong source, I mean, for the axiom. Yes. You would expect much. Yes. Okay. Are you also working on these fast radio waves? A little bit. I was involved in the original surveys that discovered them. So very few, well, not the first one, not the Lorimer